Hi everyone, welcome to new video from Nitinol Engineering. This is the third part in the series of shape memory alloy modeling using finite element analysis. If you did not see the first two videos, please have a look. I will put the link in the description box below. And in this video, we are going to solve an example of unstressed 3D bar using software Mark Mentat. In Mentat, this is how you define SMA thermostructural material model. You have to define elastic properties over here for austenite and martensite. Then the phase transformation related parameters you will define over here. These are martensite start and finish temperature and also slope. In addition, we have to define initial martensite volume fraction. Similarly, other two materials and slope for them, and here we will define G function coefficients along with Dirac volumetric part and twinning stress. Now plasticity and thermal expansion behavior is optional. If you want to define them, you can define them over here. And as you see in type 1 model, you don't have any options to choose from for plasticity definitions. But if you go to type 2 model, everything is same over here except you will get 4 options to choose from for plasticity definition. I think we have talked a lot. Now let's see one example. I'm going to keep this example very simple. In next parts, we will solve more complicated examples. We will model a 3D bar as shown over here. The dimensions of that bar is given over here. We are going to fix bottom surface and the entire bar will be at 25 degrees temperature initially. For simplicity, we are going to ignore plasticity and thermal expansion altogether. So it will have only elastic strain and strain due to transformations. For loading, we are going to apply a temperature cycle. So we are going to cool that bar to minus 100 degrees Celsius and again heat it back to 25 degrees Celsius as shown over here. So you can see total simulation time will be 3 seconds. Within first 1 second, we will cool it down from 25 to minus 100. We will hold that for 1 more second and then again we will heat it up to 25. And now you can see why I say unstressed. As bar is fixed only at the bottom and there is no thermal expansion, when we cool or heat the bar, there is not going to be stress at all anywhere in the bar. Only thing what we expect is phase transformation should occur from austenite to martensite and again martensite to austenite. These are the material properties which we are going to define. You can see here martensite start temperature is minus 45. The initial martensite volume fraction is 0. That means initially entire bar is made of austenite. So it will start converting to martensite around minus 45 and when it reaches minus 90, the conversion should be finished. That means after this point, the entire bar should be made up of martensite. Austenite start temperature is 5 degree. So when we reach somewhere over here, austenite formation will start again. And when we reach around 20 degrees, all the martensite will convert to austenite. So again, we will get fully austenite material. If we plot this loading on stress temperature diagram, it will look something like this green arrow. This is the current temperature, the initial temperature, which is 25. We are going to cool it down. This MF is minus 90. So we are cooling below MF. That's why all the austenite should get converted to martensite. Now, although we are defining the CA and CM over here, it doesn't matter because we are not introducing any stress in the model. But to have everything complete, we are going to define all the parameters. Now let's start Mentat. Once I start the Mentat, first thing I do is select current directory. So now everything what we do will be saved in this particular folder. Then let's check units. I'm going to use this millimeter, second, Newton, degree Celsius unit system. Say OK. And then let's create a solid first. For that, geometry and mesh, add solid. And over here you have to give the dimensions. So origin is 0, 0, 0. And dimension is 1, 1 and 10. So our solid is ready. Say OK. Now before we do anything else, let's save this model. I'm going to name it as example 1. And then let's mesh it. For meshing, go to auto mesh volumes. And here I will change this to hex elements. And target element size, let's keep it at 0.5. And let's mesh the part. Okay, mesh is ready. Now let's define the table. We have to define this table. Remember, temperature we have to drop from 25 to minus 100 and again back to 25. For that, go in table, new, one independent variable. Here we have to choose independent variable as time and dependent variable as temperature. Then add points. First point is 0, 25, then 1, minus 100, 2, minus 100 and 3, again 25. Save fit and check if table looks correct. It does. Then let's go back to model. Now let's define material for that new standard material. And here we will go to shape memory. In this thermostructural, here we will define Young's modulus Poisson's ratio for austenite and martensite. I gave all the properties over here. So let's do that. We are not going to add thermal expansion or plasticity, but we have to add these things. This is minus 45, minus 90, and slope is 6.666. Initial volume fraction of martensite is 0. Say OK. Similarly for austenite, this is 5, this is 20, and slope is 8.667. Lastly, we have to define G function. You can see here already some default values will be populated. I'm going to change only this one to 100. Everything else I will keep the same. And then let's assign it to all the elements, or you can assign it to solid as well. Then let's define boundary condition, fix displacement. I'm going to fix this surface over here. For that I will choose all the nodes on this end. Okay. And then for initial condition, we will define nodal temperature. Here you can put 1 and then choose the table. So that temperature will change as we defined it in table. And let's assign this to again that solid. Say OK. Next, let's create load step. Over here, I am going to define time as 3 seconds. Let's have 100 steps. Make sure load is selected. Say OK. And lastly, let's create job. Choose the load case. In job results, let's add martensite volume fraction, which is this one. And also let's add temperature. We can add stress as well, but we know stress will be 0. Displacement also will be 0. So let's say OK. It's always good to check. If we have any errors, we don't have, then go to run, save the model again and submit it. It was quick. Let's open the result file. First, let's see if displacements are indeed 0. Yep, nothing is changing. If we see the temperature is changing, but it is uniform. And also we have martensite volume fraction, which is initially 0, but as time goes on, it will go to 1 and again come back to 0. Now it's difficult to visualize over here, right? Because everything is uniform. So for that, we can do a history plot. Go to results and history plot. Then set some location. You can choose any node over here because everywhere it is same. I'm just choosing this one. Let's include all increments and then add curve. Now x-axis we can keep time, but on y-axis, let's choose that node and then choose temperature. Let's add curve, let's fit, and you can see temperature went down from 25 to minus 100 and again back up. Now let's see if the volume fraction is changing. So I'm going to clear this curve and choose this as martensite volume fraction. Add curve, fit, and yes, indeed we can see volume fraction is going from 0 to 1 and again 1 to 0. And if we overlay the temperature curve on this, when temperature is around minus 45, it starts to convert to martensite. And again, when temperature comes back to 5 degrees, it starts to convert to austenite. We have now only 2 more videos coming up on this series. The next video being bending of orthodontic arc wire. Again, we will use thermomechanical model for this. You can see the geometry over here. And this is a bit complex example because here we will induce phase transformation because of stress as well as temperature change. And in last video, we will see the mathematical model for super elasticity and solve one example using that model. If you like this video, please show your support by subscribing to this channel, which will give me motivation to create more educational videos like these. You can also go to channel's playlist tab, and here you can see all the videos with similar topics combined together. For example, let's say if you're interested in ANSYS tutorials, you can go to this ANSYS tutorial playlist and see all the videos from this playlist. All the codes and files which I use for these videos are also available for you to directly download from this channel's GitHub profile. The link of this profile is given in the description box below. If you have any questions, please let me know in the comment section below. And as always, thank you for watching.